Welcome back. My name is Jahul Alam. I am a professor of mathematics at Memorial University. In this lecture, I will be talking about Stokes theorem. So I will give you an example and solve this example to illustrate Stokes theorem. Keep in mind that Stokes theorem takes a line integral, which is the circulation of a vector field, and then converts it into a surface integral, which is the rotation or rotational flux out of the vector field, curl of the vector field, flux of the curl of the vector field out of the surface. Okay, so if we know, if we have to solve this surface integral, we can convert this surface integral and solve the line integral. Here in this example, I will be solving this circulation f dot dr on a closed circuit C, where f is 2y comma xz comma x plus y, and C is simple closed curve, which is the intersection between a cylinder and a plane. The plane is given by z equal to y plus 2, and cylinder is a unit cylinder x squared plus y squared equal to 1 for every z. So that means you can imagine that if you take a cylinder and if you take a cross section with a slanted plane, then you will get an ellipse. Okay, so as you can see that in Stokes theorem, you have to solve the surface integral. In the present case, you are given the line integral and you are expected to convert the line integral into the surface integral and solve the surface integral of the curl of the vector field. So let's first calculate curl. So to calculate curl, you form a matrix, and by putting the unit vectors I hat, j hat, and k hat on the first row, and then the partial derivatives on the second row, and the vector field f on the third row, which is 2y xz x plus y, and you can easily find the vector, find the curl of this vector field by calculating the cofactor, 1 minus x minus 1 z minus 2. Okay, maybe you can just take a minute and cross check that and let me know if I have made a mistake. Okay, so your next step is now to solve the surface integral. So we want to solve now curl of f dot ds, or maybe you can write curl of f dot n hat ds. So ds is a vector element and curl of f is a vector. So we will parameterize the surface. So now what is the surface here? So maybe if we try to get an idea schematically, so take a look at a cylinder x square plus y square plus x square plus y square equal to 1 for all z, so vertical cylinder. And then if you take a cross section, it might be something like that. So that cross section would be this surface, which is the A. Okay, and then if you can look at this section of the sphere, its projection is just a unit circle on the bottom of the cylinder. So by looking at this configuration, I can think of parameterizing this elliptic surface using kind of polar coordinate. But now I will use the symbol of generalized coordinate. In the polar coordinate, generally we use r theta, but let's say maybe we can just keep the symbol in the generalized coordinate u and v. So u is a parameter, v is a parameter, and those parameters you are looking for the position vector x, which you are considering as a function of u and v. The second component of the position vector y, which is a function of u and v, and the third component also a function of u and v. And I'm going to think this as u cos v, u sin v, and then z I'm going to find it somehow from the given surface. So let's look at what is the given surface. I have x square plus y square equal to 1, which might give me the parameter domain, and because I'm looking for z, here is no z, so this surface has z equal to y plus 2. So that tells me y is u sin v plus 2. Okay, let's figure out the parameter domain. So u cos b plus u sin v, which are x and y. So x square plus y square would be u square cos square v plus u square sin square v equal to 1. So which means u will be going from 0 up to 1. Okay, and then theta, which or v is like theta, which is going from 0 up to 2 pi, because we have the full cycle of the cylinder, and cylinder is centered at origin. Okay, so now I have this parameterization. I can differentiate with respect to u. So r sub u, which is cos v sin v and sin v. Okay. If I differentiate with respect to v, r sub v, so I will get negative u sin of v, positive u cos of v, and positive u cos of v. Okay. Good. So now what I will do is that I will take a dot cross product. I'll take a cross product. Okay, so let's just make some room. Okay, I'll take the cross product r sub u cos r sub v, and again the cross product would be straightforward here by looking at this. So you look at this cofactor and then you take those two columns and then you take those two columns. So that is very clearly coming from 0 comma u comma u. And again I'd say that maybe you can just verify whether this cross product is accurate or not. That's straightforward. So let's focus on not on the calculation, on the procedure. So once you have the cross product, then everything is ready. So you think of, okay, so in Stokes theorem I have to calculate the circulation after dr. That is my given problem. So I write this, or I think of curl of f dot ds by using Stokes theorem. So I convert the line integral into a surface integral, and then I got the surface integral into the parameter domain. So curl of f, I have calculated that right here 1 minus x minus 1 z minus 2. X is u cos b, y is u sin b, z is u sin b plus 2, but here is no y, so don't worry about the y. So let's just write that down. So 1 minus x. So what is x? U cos b. U cos b. Second component is just negative 1. Third component is z minus 2. So what is z? Look at the u sin v. U times sin v plus 2 minus 2 cancels out. Okay, so maybe I just make some room here for clarity right down there. Okay, so the dot product of RU cross RV, where RU cross RV is 0, comma, negative U, negative U. Okay, and then you write down dA or du dv. So now also put the limit. So let's put the inner integral for u 0 to 1, outer integral for v 0 to 2 pi. Okay, so this one is straightforward. I have to do a dot product, and you can see the on the right vector first element is 0, so that makes things simple. Second element is minus 1 times minus u, which is u, and then the third element is u sin v times u, so plus u square sin v du dv, right on that. Okay, so let's do one at a time. So the inner integral, you can that's a iterated integral, and perhaps it is separable, so you can do it at once. But let's first solve the inner integral for clarity. So half u square plus 1/3 u cube sin b stays as is. Okay, the limit is from 0 to 1, and still you have to integrate from 0 to 2 pi. Okay, good enough. So now you substitute 1 for u. So for the variable u, you get half u square, half 1 square plus 1/3 u cube, so 1/3 1, and then you have sin v. Okay, and then if you set u equal to 0, don't worry about that, because that's 0 is 0. Okay, so dv 0 to 2 pi. So now this integration is with respect to b half. So when you integrate half with respect to b, is half b plus 1/3, but you integrate sin b, antiderivative is negative cos b, so you get a minus sign, 0 to 2 pi. So the first term is half b, half times 2 pi minus 0. Second term is 1/3 cos b, so 1/3 times cos 2 pi, which is 1, minus cos 0, which is 1. So the final result is pi. Okay, so that's straightforward. So you can perhaps go back and review what I have just presented. In this example, we have a circulation, and we have to evaluate the circulation using Stokes theorem. So we convert the circulation into a surface integral by using Stokes theorem, and then we use our knowledge of surface parameterization, convert the surface integral into a standard classical double integral and then solve the double integral. So maybe I give you another exercise here. So in this exercise, we are going to apply Stokes theorem. Apply Stokes theorem to solve the integral. To solve the integral f dot dr, where the vector field f is, let me write that down for you, x, y square is the second element and z square is the third element, and C is a positively oriented simple closed curve. Positively oriented simple closed curve. That is the intersection between the plane x plus y plus z equal to 1 and the cylinder, x square plus y square equals 9 for every z real number. Okay, so this exercise and previous exercise is a very similar one. So if you understand what I have presented, you perhaps would be able to solve this one. The only difference is the curve of intersection. Again, the curve is very similar. The cylinder intersect with a plane. Okay, cylinder intersect with a plane. Now the cylinder this time is a cylinder of radius 3, but again centered at 0. So the calculation process for this example is the same as the previous one. Give it a try, and if you have any difficulty or if you have any question, please contact me, or if you want to verify the answer, you can also contact me. Thank you very much.